Oh, what is the time? We can start?
Yes, yes.
Sorry, sir.
Oh, okay. Uh, Good evening, dear friends. Let us start our seminar. I am very glad to introduce our today's speaker is Nishant Rathee from IISER Mohali, India, and the title of his talk is Extension of Skew Braces. Please.
Thank you. Just, uh, uh, Thank you very much for this opportunity. I was postdoc in IISER 1 year before, so now I joined this ISI Delhi. So now I'm postdoc at ISI Delhi, so not at IISER. So yeah. Okay. So let me tell you what I'm going to talk. I'm going to talk about the extensions of skew braces. Um, so let me start with some background. Why we study the skew braces? So suppose you have a set X and you have a bijective map from X square to X square, such that it satisfies the this braided relation, the R cross ID composed with ID cross R, composed with R cross ID, and then you flip the middle one to the corner one, ID cross R composed with R cross ID, composed with ID cross R, where R cross ID is a map from X cube to X cube, such that R is acting on in R cross ID. R is acting on the first two component, and the last component remains as it is. And ID cross R is a map from X cube to X cube, so that R is acting on the last two component. So if you have such a map, then we say that this is a solution of Yang-Baxter equation. The equation is arising from physics. Uh, but like we will go, but it have lots of interesting mathematical aspects. Okay, so let us see some examples. So take the flip map, xy going to yx over any set. This will always be a solution. Suppose you have a set x and you have two permutations of x such that they commute. Sigma tau is equal to tau compose sigma. Then you define the map R such that xy going to sigma y comma tau x. Then this is also a solution of Yang-Baxter equation. So, okay, so let us define what do we mean by non-degenerate solution. So when you have a map from x square to x square, you can always decompose them in the form of coordinate maps. So when you have a map from x goes to x, you can write it rxy in sigma x comma tau y, where sigma x and tau y are mapped from x to x. So if these coordinate maps are also bijection, then we call them call the solution to be non-degenerate. So as you can see, identity map is also a solution of this equation, this Yang-Baxter equation. But in the case of identity, if you take R to be identity, the coordinate maps will not be bijection. So that is not non-degenerate solution. So we'll basically talk about non-degenerate solution because they are the most interesting one. Okay, so this is what do you mean by non-degenerate solution. So now I have defined non-degenerate solution. Now let me define an algebraic structure, and later we'll talk about what is the relation between this algebraic structure and the equation. So an algebraic structure E plus circle, where both E plus and circle are groups, such that they satisfy the following compatibility condition: A circle B plus C is equal to A circle B minus A plus A circle C, where minus A represents the inverse of A with respect to the plus operation. So if you have such a triplet, then we call it as skew brace. The group E plus is called the additive group and E circle is called the multiplicative group of the skew brace. So please note that this plus doesn't need not be the abelian group always. This could be non-abelian. So, but it is super convenient to write it as a plus operation and do calculation. So yeah, we write it as a plus, but this need not be the abelian group. Okay, so let us see some examples. So all groups with same plus and circle operation are the examples of skew braces called trivial skew brace. So when you take the plus and circle to be same, then this A and A will cancel out and you will left with A B dot C. And here also you will left with A dot B dot C. So all the all groups are trivial skew braces. So let us see some non-trivial examples. Suppose you have a group G, then you define circle operation to be the opposite group operation of G. X circle Y is equal to Y X, and X plus Y is the usual group operation. Then this will also be a skew base structure over G, something called almost trivial skew base. So note that if G is an abelian group, this is just a trivial skew base structure over G. Okay. So, okay, so if a trivial skew base is abelian with an abelian additive group, then we call that to be a trivial base. So this is an analogy we'll be using in this talk. When we say the trivial base, it means just an abelian group. So all radical rings. A radical ring is a ring such that Jacobson radical, which is the intersection of all maximal ideal, is equal to the full ring. Then over radical ring, if you define the circle operation to be a circle b is equal to a b plus a dot b, then it is an example of a skew base with plus operation is the plus operation of the ring. Okay. One more example. So let P be a prime number, then let ZP square be the cyclic group of order P square, the ring of integer model of P square. Then you can define the circle operation to be a circle B is equal to A plus B plus PAB. And then this defines a group operation over ZP square, making this to be a skew base. So these are some examples of skew bases. So we start with an equation, then we start with an algebraic structure. Now let me tell you what is the relation between them. Okay, so before that, one more property of a skew left brace. So if you have a skew left brace, then you can define a group homomorphism from the multiplicative group to the automorphism of additive group by this lambda map. Lambda A B is equal to minus A plus A circle B. This map is called the associated lambda map with the skew base, or sometimes it is called gamma map. Uh, so in this talk, we'll call it to be lambda map. So in case of skew bases, this map turns out to be a group homomorphism, and we call it the action of additive multiplicative group on the additive group. So okay. So this is a very fundamental theorem which connects the skew bases to the Yang-Baxter equation. So if you have a skew left brace E, then the map defined from E cross E to E cross E by this RAB is equal to lambda AB, and by this complicated formula lambda inverse lambda AB is equal to minus A circle B plus A circle B. Then this defines a non-degenerate solution of Yang-Baxter equation. Furthermore, this solution is involutive if and only if the additive group of the skew base is an abelian group. So this is the relationship between the skew bases and the Yang-Baxter equation. So okay, so actually the converse is also holds. If you have a non-degenerate solution, then you can also define a skew base, but the correspondence is not one-to-one. So the construction is a bit technical. You define a structure group of the solution, then you define AXR and GXR and define a bijective one cocycle and induce a skew base structure over the such that the structure group will be the multiplicative group of that skew base. So we'll not talk about that, but this is the analogy. This analogy also holds. Okay. So, okay. Please note that if E is a trivial skew base, then this minus A and this A will cancel out, and you're left with lambda AB is equal to B. So if E is a trivial skew base, then this lambda map is just an identity map. So this lambda will be a trivial homomorphism. So if E is a trivial skew base, then lambda AB is equal to B, and lambda will be a trivial homomorphism. So now let me introduce you with the substructures in the category of skew bases. So a subset of a skew base C is called skew base, sub-skew base, if it is closed under both of the operation, like it is closed under with respect to plus and closed under with respect to circle. So basically it should be subgroup of plus as well as the subgroup of the multiplicative group. So that is called sub-skew base. So ideals are the interesting in this category. So suppose you have a skew left brace E, then a set I is called an ideal of E if it is normal subgroup of E plus, a normal subgroup of the I-circle multiplicative group, and it is invariant under the lambda map for all A belongs to E. So lambda AY belongs to I for all A in E and Y in I. So uh, these are called the ideals in the category of skew basis. Uh, so let me introduce you with the very important class of ideals in the category of skew basis. The first one is the SOCAL, which is the intersection of the additive group with kernel lambda. Kernel lambda is the uh, kernel of the homomorphism lambda, and annihilator is further shrinking the SOCAL by taking intersection with the center of the multiplicative group. So these two, of course, this proving that this circle is an ideal, it requires some calculations, but these all proved by Benjamin in his paper. So these two are very. So this annihilator also sometimes people view as a analogous of center in the category of skew bases. So in this talk we'll see why it is called so. So these are the examples of ideals in the category of skew bases. Um, so of course, if we have a trivial base, then all the normal subgroups are the ideal. So that's it. So okay. So if you have an ideal, then you want to define the quotient. So if you have an ideal E, then you can define the quotient to base E by I. So you define E by I to be the okay. So you take the you can view this. You have this I to be the normal subgroup of E plus. Then you can use naturally induce the circle operation through E, and as E is invariant in lambda, so that will be again be a skew base. So if you have an ideal, then you can quotient it, and the quotient will also be a skew base. So okay, so let me tell you what are the skew base homomorphism. So if you have a two skew base E and H, then a map F from E to H is called a skew base homomorphism if it respects both of the operation. So these map are called the skew base homomorphism. So injection and isomorphism also defined in the similar manner. If F is injective, then we call that is an injection. If F is bijection, then we'll call it an isomorphism. So okay. Uh, so if you have skew-based homomorphism, then the kernel of a skew-based homomorphism will also be an ideal of E. So very something very similar to the category of groups. So in the category of groups, kernels are always the normal subgroup. So same here in the category of skew bases. And yeah, image of a skew base under an homomorphism will be a sub-skew base of H. So yeah, so let us come to the extension. So if you have an ideal E, such that we see that E by I is again a skew base, such that E by I is isomorphic to H, then we say that E is an extension of I by H. Equivalently, we can represent an extension by short exact sequence by I H, where pi is the natural projection of E on H. So if you have an extension, sometimes we always thought this as a short exact sequence of skew bases. So this I we always view as a ideal of E. So this is natural inclusion of I inside E. So we don't write anything here, but this is natural inclusion of I inside E. So okay, so when you are
Mhm. Sorry, I cannot listen you. Nishant.
No, no. So, like, I need to start from the starting, or is it? I can continue from there.
I think you can start with this slide because I remember the definition of extension.
Okay. So, so we define what is a split extension. So okay, the extension of E of H by I split if and only if there exists a subscript base K of E such that K plus I is equal to E and their intersection is the zero element of the skew base. So the proof is really simple. So suppose you have a split extension, then there exists a section S from H to E, which is a skew-based homomorphism. And you remember when we have this pi composition S is identity map. So when this pi composition S is a bijection, this S will always be an injection. So this S is also is actually an embedding of H inside E. So we can take this K to be the SH. So and this using that this I is in kernel, so we can see that this K intersection I is zero. So uh, this show that the complement exists in this case. So conversely, if you have such a K satisfy this K plus I is equal to identity and K intersection I is equal to zero, then you can see that pi restricted to K is an isomorphism. Pi restricted of skew bases. As because I is always in the kernel and K is the part outside of the kernel. So you can define the section to be the pi inverse K. So which will be the required section. So such a subscubase K is called the complement of I in E. So very similar to group theory. So a skew-based extension splits if and only if there is a complement of I in E. Okay, so let us now we see that how a base acts on its ideal. So like when you talk about the category of groups, so a normal subgroup to be which is something closed under the conjugations. But in the case of bases, you have three conditions. Like it should be the normal subgroup of the additive group, multiplicative group, and it should be the invariant under the lambda map. So here it comes the three actions on its ideal. So suppose I be in trivial base. So we consider I to be trivial base because these are the most interesting one to view the action of a skew base. Because in general, even in the groups, the action doesn't behave nicely on the non-abelian groups. So we take the I to be the trivial base, and let S be the section of the extension, and then for all H in H and Y in I, you can define three maps: nu, sigma, and mu. Where nu, sigma are the maps from H equal to the automorphism of I plus, and mu is a map from H plus to I plus, defined by this. This mu is the action of I corresponding to the lambda map, as it is invariant under lambda map. So this part always belongs to I. Mu is the action of H corresponding to the additive groups, and this sigma is the action of H on I with respect to the multiplicative groups. Okay, so these are the actions of a skew base on its trivial ideal. So for a given set theoretical section S, the map mu is an homomorphism, while this mu and sigma are the anti-homomorphism. So we have defined this way. So we have taken inverse first. If we reverse the inverse, then they will be homomorphism. But in our case, we take them to be the anti-homomorphism because in this setting it is easier to do the calculation. So we have adopted this notation. So this nu is an homomorphism, while this mu and sigma will be anti-homomorphism, and each nu, mu, and sigma are the independent of the choice of a section. So this mu and sigma are independent of choice of a section. It follows from the group theory because these are the action corresponding to the group extension induced by a skew base extension. So these will always be independent of choice of section. We only see that this new map is independent of choice of section. So okay, so the map mu and sigma are independent of choice of section from the extension theory of groups. To see that the map mu is independent, let S and S dash be two sections. Then for all H in H, we know that two sections are differed by an element of Y. So you can write this S dash H to be SH plus YH. And then mu dash H, let mu dash H is the action corresponding to S dash H. Then mu dash H is equal to lambda S dash H plus lambda S H plus YH. And you can, using the skew base property, you can always transform this plus operation into the circle operation, and still this ZH will be in I. And using that I is a trivial base, this action is just identity. You will left out with this new HY. So this shows that these actions are independent of the choice of the section. Okay. So now further we see that the compatibility condition between the actions. So let H1 and H2, H3 be in H and Y in I. Then using the compatibility condition of skew basis, you have this following relation: this SH plus Y circle SH2 plus SH3, and then you can expand it using the compatibility condition of a skew base. So simplifying both sides, one can verify this mu sigma satisfy the following condition, following compatibility condition. So the first condition is that you applied this lambda h h3 to on mu, and it will flip with new h, and this lambda h1 h3 will become this mu h3. And the second condition is a bit complicated one. So this new h1 plus h3 sigma h2 h3 plus y plus mu h3y is equal to this thing. So this so if so this action corresponding a skew base extension, you always satisfy these two conditions. So in general, if you have a action mu and sigma and it satisfy both 4 and 5, then we call such an action to be a good triplet of action. Okay. So, one can see that if I is an annihilator of V, then this action is just trivial, because the action of lambda is just trivial, and this I sit inside the center of both of the groups. So this action mu and this mu and sigma will also be trivial. Okay. So now let us come to the groups part. So if you have a skew base H, then you have action of the multiplicative group on the additive group, which allows us to construct the associated semi-direct product group lambda H, defined by this action lambda. And if H is a trivial skew base, then the map, this lambda is a trivial homomorphism, and you okay. So this is so this is typo. Should be just a diamond. So in case of trivial skew bases, you just get a direct product. So this lambda is a typo. Sorry about that. So okay. So now suppose H and E are skew bases, then every skew base homomorphism from H to E induces a group homomorphism from the lambda groups defined by this. So yeah. So if you have a skew base homomorphism, then you can induce a homomorphism of lambda group by this F cross F. So this F cross F is a map, so that F cross F xy is equal to Fx comma Fy. Okay. So this shows that this lambda is a functor from the category of braces to the category of groups, such that under which H going to lambda H and a morphism F going to F cross F. Furthermore, if you have an ideal I of E, then this is proved by Cindy Tsang in his paper, The Representation Theory of Skew Bases. Then lambda I is a normal subgroup of lambda E. This is not difficult to prove, but it requires some manipulation. So if we have an ideal of E, then corresponding lambda group will be a normal subgroup of lambda E. Furthermore, you can see that this quotient will be isomorphic to lambda of E by I under the natural map x y bar going to x bar comma y bar. So this tells that this functor is actually exact. Like exact functor is which maps short exact sequences to the short exact sequences. So Now suppose you have a skew-based extension, then you can always construct an extension of lambda groups by this way. So in this case, we are not even assuming this I to be like there is no need to assume this I to be a trivial base. This happens for all skew-based extensions. So if I is a trivial base, then this lambda I will be I cross I, because lambda is just a trivial homomorphism, and we'll get an abelian extension of corresponding lambda groups. So abelian extensions are the most interesting extensions of the groups. So throughout this talk now, we'll assume that this I to be a trivial base. Furthermore, one can see that this annihilator of E uh, sits inside the center of this lambda group. This annihilator of E cross annihilator of E is in Z of lambda E. So if you have an annihilator extension, like annihilator extension is when this I sits inside the annihilator of E, then you will end up with a central extension of lambda groups. And there's alternatively we can see that if this I is in annihilator of E, then action is trivial. So an extension is central extension if and only if the action associated action is trivial. So from that also we can see that annihilator extension induces the central extension of the lambda groups. Okay, so now this is also the result from the ongoing work with my PhD supervisor. Suppose E be an extension of a skew base H by an abelian group I, where I is considered as a trivial base. Suppose the extension has associated good triplet of action mu sigma, which we have defined this mu corresponding to the action of additive groups, mu corresponding to the action corresponding to lambda, and sigma corresponding to the action of multiplicative group. Then you can define the right action of the group lambda H on I cross I corresponding to the group extension lambda E is given by this formula, this weird complicated formula, where this Hg acts on xy by this mu inverse G mu H x minus y plus mu inverse G mu H sigma hy comma sigma gy. So how, suppose you have a let S be a set theoretical section of the skew base extension E, then you can easily see that this S cross S is a section of the corresponding lambda groups, and this where this S cross S is defined by this coordinate map S cross S at G is equal to SH comma SG. Then like for compute the extension action of a corresponding of a group extension, we need to calculate this conjugation. So this SHG comma SHG inverse XY SHG SHG. So we need to compute this inverse in the lambda group, and solving this we can easily see that the action of the lambda groups will be this. This is completely determined by this action of skew base extensions. Okay, so okay, this also shows that this action is this action of the lambda group, the group lambda H on I cross I, depends on the good triplet of action mu sigma, not on the choice of an extension E. Okay, so furthermore we have result. So suppose that H be a skew base and I be in a abelian group. Let mu sigma be any maps on OT I, where mu and sigma we have discussed above. Then this is the map chi from this lambda H to the automorphism of I cross I, given by the same formula, is an anti-homomorphism if and only if this mu sigma is a good triplet of action. So actually this the compatibility condition among the good triplet of action is actually turns out to be a condition of a group homomorphism from the lambda groups, or the action of lambda group on the I cross I. So the proof is really simple. So if chi is an anti-homomorphism, then by restricting the action of chi h to I cross 0, we obtain the first condition of good triplet of actions. And moreover, solving this chi h0 composite with chi 0, as this is anti-homomorphism, so you can reverse this chi g plus h. So you can verify, you can obtain the second good triplet of actions. And converse is really easy. So if you have a good triplet of actions from H to I, Then we construct a skew-based extension of E of h by I. This is something we have done uh, in our first paper, and explicitly the extension is given by this formula. So the additive group of this extension is defined by this formula, and the multiplicative group is defined by this formula. Actually, we have taken the two cocycles to be zero. This could be defined in more general way, but the thing is, like, if you have a good triplet of action, then you can define an extension of E by H such that the associated good triplet of action is exactly the same. And we know that corresponding, if the good triplet of action is nu mu sigma, then we can always construct a right action of the lambda H on I cross I, given by exactly this formula. So okay. So we have a well-defined map from the extensions of skew base h by I to the group extensions with respect to action chi of lambda h by I cross I. The map is given by E going to the extension of lambda I. So we have a well-defined map between the extensions. So this is the main result of the paper. So the thing is, if you have a skew-based homomorphism, then you can always induce a homomorphism of corresponding lambda groups. But conversely, not always be true. So if you have a homomorphism of corresponding lambda group, you may not induce a map at the level of skew bases. So, but something partial we can do in case of Sokal extension. This is what this result is mainly about. So, suppose E be a Sokal extension of H by I. This means that I is contained in Sokal of E. Then this E is a split extension if and only if corresponding lambda extension splits. So, one way is easy to see. If skew-based extension splits, then the section S cross S will always be a group homomorphism at the level of lambda group. You can always make the group extension splits, but we only see the converse part. So assume that the group extension lambda E splits, then there exists a section group homomorphism S from lambda H to lambda E, such that pi cross pi composed with S is equal to identity on this lambda H. Um, so now this S is a map from this lambda H to lambda E. This lambda H is set-wise is just S cross H cross H. So you can break it down into the coordinate map. So this SHG, you can always write this in the form of coordinate map S1HG, S2HG. Since S is a homomorphism, then for H1 G1 and H2 G2 belongs to G, we can expand it like this. This is basically the group operation on the semi-direct product, and using this coordinate map we can expand into this. So comparing the first coordinate, we obtain this, the S1 H1 plus lambda G1 H2 G1 circle G2 is equal to this S1 H1 G1 plus lambda S2 H G1 and S1 H2 G2. So this is actually very close to be a group homomorphism. So to close to a skew-based homomorphism, we just need to replace this S2 by S1. So you can do this by utilizing the fact that this S2HG minus S1HGH will always be in I, because when you apply pi to S2GH, you will end up with H. Then you apply, so you will end up with G, and you apply pi to S1GH, you will end up with G. So this will always be in I. So this element will, and we know that I is in Sokal I. So you can actually replace this S2 by S1. Of course, this requires some more manipulations, but this is sketch of the proof. So we can see that this map H going to S1 H comma 0 is a skew-based homomorphism from H to E, which will be the required section of the extension E. So in very particular case of Sokal extension, we can induce a map from the level of lambda group to the skew bases. So okay, so now we talk about the extension. We talk about the lambda group extensions, and now let comes to the second cohomology group. Let H2SB as remains skew base. Hi denote the second cohomology group of skew base H by I with respect to a fixed group triplet of action of nu mu sigma. Explicitly, this second cohomology group consists of the pair beta comma tau, such that beta is a 2 cocycle from H plus to I, and this tau bar is a 2 cocycle from H circle to I, such that tau bar is given by this tau bar H1 H2 twisted by the action nu. So this is something we have done in our first paper extensions of skew bases, and further this satisfies the following compatibility condition, this weird relation. So basically the second cohomology group of a skew base consists of a additive 2 cocycle and a multiplicative 2 cocycle plus a compatibility condition among them. So that is what the second cohomology group of a skew base. Let H2GP lambda H I cross I denote the second cohomology group of the group lambda H by I cross I with respect to the action chi induced by the good triplet of action mu sigma, which we have seen earlier. So then we know that there is a bijection between the extension of skew braces with the second cohomology group, and there is a bijection between the extensions of second cohomology of groups between the extension of groups. So, and these extensions are very particular in such a way that split extension corresponds to the identity elements of the respective cohomology group. So, under this bijection, split extension goes to the zero element of the cohomology groups. So now we have seen that we have a association E going to the equivalence class of E, going to the equivalence class of lambda E, from the at the level of extensions, from the extension of skew bases to the extension of lambda groups. So we got an association at the level of extension, but we know that there is a bijection between the extension and the second cohomology group. So we can induce this association at the level of cohomology group of skew base to the cohomology group of lambda groups. So this association, this needs some calculation, but precisely under this calculation, a two cocycle beta comma tau goes to this phi beta comma tau bar, where this phi beta comma tau bar defined by this way. By this complicated formula. So this is somewhat complicated formula you obtain when you explicitly try to compute this association at the level of second cohomology groups. Okay, so we, in case of Sokal extension, so one can easily see that this map phi is actually a group homomorphism. So again, this required some calculations, but this map phi is an group homomorphism. So in case of Sokal extension, this map phi is injective. So as we see that this extension of skew base split if and only if the extension of corresponding lambda group splits. So, and we know that under this association, split extension goes to the identity elements. So an element belongs to the kernel if and only if corresponding skew base extension splits. But if the corresponding skew base extension splits, then the corresponding group extensions also needs to be split. So the element on the right hand side is always 0. And conversely, if some non-zero element is going to 0, then this means that some non-split extension going to split extension, which we have seen that cannot happen. So in case of Sokal extension, this map phi is injective. So in case of Sokal extension, you can actually embed this second cohomology group of skew base inside the second cohomology group of lambda groups. So, and in general, this association E going to lambda E is not injective in general. Using gap, we find a skew base. There are actually many skew bases, but I'm telling you the most simplest one. We find a skew base A of order 8, such that in which there is an ideal I of order 4, such that I does not admit a complement in A, while this lambda I does admit a complement in lambda A. So when you have a complement, this means that the extension split. So if at the level of skew base it doesn't admit a complement, this means that the skew base extension doesn't split, but the extension of lambda group splits. So this association is not injective in general, But in case of Sokal extension, this map is injective. So let us see some applications. So an ideal I of skew base is called whole ideal if the GCD of order of I with the GCD with the order of E by I is co-prime, then we call such an ideal to be a whole ideal, something very similar but we define the whole subgroup for groups. So then we can see that if I is a whole ideal of E, then lambda I is a normal subgroup, normal whole subgroup of lambda I. And by Sur-Zassenhaus theorem, we know that the extension lambda E of lambda I always splits. So and the extension of E of I always splits. So so this shows that every whole ideal which is contained in the Sokal of a skew base always admits a complement. Actually, we prove this result in much more generality using the non-abelian cohomology. But like this is the direct application of the embedding of second cohomology group of skew bases into the second cohomology of lambda groups. Furthermore, this second cohomology group H by C star is the second cohomology group of skew base H with coefficient in C star with trivial action. It's something called the Sur multiplier of H. So this is defined by Van Ramen. So in case of Sur multiplier, we have this embedding because we see that the action is trivial, then this action is annihilator, and annihilator is actually contained in Sokal. So in this case, this map phi is in the case of Sur multiplier, this map phi is an embedding, and further this action is trivial. You can decompose uh, this second cohomology group into this because this cohomology functor is distributive on the modules. So you can break it down into the direct product of Sur multiplier of the group lambda H. So and it is well known that the group this H2 lambda H C star is a Sur multiplier of group lambda H, and its exponent is okay. So this is a typo. This exponent always divides H square. So this the exponent of Sur multiplier always divide the exponent of the group. So hence we can from here we can deduce that the exponent of Sur multiplier of skew base always divide the order of H square. Thank you.
Okay, let us thank the speaker for interesting talk. Any questions, please? Questions, suggestions? I have a question. In your definition of split extension of skew braces, is it true that you have split extension of additive group and also split extension of multiplicative group? Is it true or
So
not?
yeah, yes. Because by definition is that there exists a section which is a skew-based homomorphism. So a skew-based homomorphism is a homomorphism with respect to both additive group and multiplicative group. So so yeah, the additive group extension and the multiplicative group extension always splits. If I say that my skew-based extension splits.
And if you forget about some structure, for example, multiplicative structure, you will have split extension of additive group. And
Yeah,
if you forget about additive, you will have extension of multiplicative group, split extension. Is it
yeah.
correct? Okay,
Uh,
thank
so
you.
yeah,
Uh,
so uh, yeah, your question is definitely true. So uh, like so when your skew-based extension splits, then the both of the extension of additive group and multiplicative group splits. But the extension of if the extension of multiplicative group and additive group splits separately, then you cannot deduce that the skew-based extension splits.
Yes, yes, of course, it's need to some new conditions there. You're right. But and also the second question, you construct a functor from the category of split extension to a group semi-direct product.
Yeah,
Is it correct? But if now we consider not split extension, some extension of skew braces, is it possible to define the similar functor and we construct some group also?
I don't understand you. I have a functor from the
See,
category of skew basis to
you
the category of groups.
you construct a functor from the category of split extensions to the semi-direct product of groups.
No, 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 no. So
No.
the functor is from the category of skew basis to the category of groups. Oh, okay, okay, okay.
Ah,
I got you. Yeah, okay, okay, yeah. Uh, 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 actually, so okay, so I don't know whether I answered your question. So like the speed extension of skew basis always goes to the speed extension of the lambda groups.
yes, but if you consider some extension, you construct some extension of skew braces. Is it possible to define some type of group? Maybe not semi-direct product, but some extension of one group with another group. Or you consider only split extension of skew braces.
So like split extensions of skew basis always goes to the split extension of groups, uh, like under the lambda, under the funder lambda. But I never thought about some another funder like this.
Ah, okay, you didn't consider. Thank you for interesting talk. Other questions? No. Let us thank speaker again. How is Manoj?
He's good, sir. He's
Okay.
in Allahabad. I am in Delhi now.
Ah, in Alabama. Okay. Please say hello to him.
Have you visiting India anytime soon?
I hope. Okay. Thank you. Thank you. Bye bye.
Well,